Hello. We will begin our introduction to thermodynamics with a discussion of the first law. In this particular discussion, we're going to go through basic definitions of energy, and from that we need to talk about work and heat, and then finally get into a little bit more detail about energy and something called internal energy, and this will be the energy of individual atoms and molecules and how that relates to the temperature of the system, which also relates to something called the equal partition theory, which is a classical theory which helps us to determine average energies based on the temperature of the system. And then finally, we'll end with the basic mathematical definition of the first law of thermodynamics. We start with the universe. Wow, that's an awfully big thing to start with. How are we going to narrow it down to our little world and our little system under study? Well, we just simply use the term universe when talking about the thermodynamics of systems. And the system is defined as whatever it is that we are studying, trying to do a calculation for. And this is necessary, as we'll see later on when we talk about the thermodynamics of processes and whether they happen or not. We will need to distinguish between what we're studying, the system, and the surroundings, which, as you can guess, is what surrounds the system. And again, this may seem trivial, but it is important from a thermodynamic perspective that we lay out these definitions so that we know when we're doing computations what exactly it is that we're calculating. All right, so let's get back to energy and ask the basic question: what is energy? This is something that is actually quite deep if you start to think about it. The term energy is something that we use every day without really thinking about what exactly it represents. And so we need to actually have some definitions here when we think about that. So the basic qualitative definition of energy is the capacity to do work. Okay, well, that's all fine and good, but that means we need to know what work is. And again, this is a term that we use on a regular basis in a very qualitative, vague way. But again, since we are going to be doing calculations, we need to be able to define it mathematically. Well, you may remember from your physics class, and we use the symbol W to represent work, that work is equal to force times distance. That is, that when we have an object, the work required to move that object is equal to the force that we apply multiplied by the distance over which it's moved. So that's simple enough. And so here's a basic finite definition of work. Of course, we're going to be dealing with situations where things are changing, perhaps as we're moving them, and we need, therefore, to use in calculus a differential form of the equation many times, and we just simply indicate that with the d here. So the more precise definition of work is dW is equal to F force times ds, where ds represents distance. And again, dW and ds represent infinitesimal amounts that we'll have to deal with when doing calculations. And of course, to go from the infinitesimal to the finite, we will have to use integration. It's basic calculus. Aren't you excited at this point? So we're not going to get into that in this video, but we're just going to start laying out all of these definitions. Okay, so breaking down energy a little bit more, when we talk about energy, we talk about kinetic energy, which of course is the basic energy of motion. Okay, and we represent kinetic energy with the symbol T, as seen here. Okay, so then within this equation, and you of course no doubt recognize this equation from physics classes and other discussions you've had, the 1/2 mv squared, the m represents the mass of the object being that's undergoing motion, and of course v represents its velocity in meters per second. So using, of course, SI units, which we must also always be aware of units and how we're using them. We'll note, of course, that mass has units of kilograms, and velocity will have units of meters per second. So when we take the product of these units, the total, 1/2 mv squared, is going to have units of kilogram meters squared per second squared, since we're squaring the velocity. And of course, you should know that this corresponds to the SI unit of energy, which is the joule. So that, of course, was the kinetic energy, which is the energy of motion. We also, as you know, have potential energy, which is the energy of interactions. And so some basic interactions that, of course, you've been exposed to. Potential energy, mgh, is gravitational potential energy associated with an object of mass m at some height h. Its potential energy is m times g, g being the gravitational constant, times h. Again, you should recognize that from your physics class, that's the gravitational interaction and potential energy associated with that. More important for chemistry and the systems that we're going to be looking at is a Coulombic potential energy, which is the energy of interaction between charged particles, particles of charge Q1 and Q2. Their interaction is given by, potential energy of interaction is given by this expression, and R represents, of course, the distance separating those particles. And this is something we'll get into in much more detail later on, particularly when we get to atoms and molecules and actually quantum mechanics. All right, so we talked about energy now and basic definitions. Let's lay out some information about work and heat. And again, we'll be going into much more detail in later videos, but again, you'll remember work, as we mentioned earlier, is the force applied to an object times the distance that object is moved. And again, work represents kind of an ordered form of energy. It's directed energy, because we are directing and moving an object through a distance s, as indicated earlier. And then, of course, there's also heat when we talk about energy. And whereas work is an ordered form of energy, heat is kind of disordered, random motion, particles moving about in random ways. And that is, how we look at heat. When we talk about work and heat, we're going to be talking about how work and heat will change the energy of our system. So we'll be looking and doing calculations where we're calculating the energy changes that occurred when we do work on the system, or the system does work, or when we are heating something. Heating involves energy transfer, and so we're going to be calculating those changes that occur when we do that. All right, so let's get into a little bit more detail. When we talk about energy, we're going to be focusing on molecules and atoms, and with molecules and atoms, we're going to be talking about something called internal energy, which is the energy of those molecules and atoms, and we represent that by the symbol U. Now, there are several different types of internal energy that we'll be focusing on through our discussion in thermodynamics and quantum mechanics. Translational energy is just simply the energy of motion through space. As particles move through space, they are translating. And of course, the kinetic energy of those particles as they move through space is 1/2 mv squared, as we mentioned earlier. There's a rotational energy, which is also kinetic energy. In this case, the particles aren't moving through space, but they are tumbling, rotating in space. And this will be applied to molecules only, because as molecules can tumble, diatomic molecules can tumble and can rotate. So there's a rotational energy associated with that. And then vibrational energy, again, we apply this to molecules. And vibrational energy, we're talking about bonds stretching, or we have bond angles changing through bending types of motion that you've no doubt talked about in other chemistry classes. And again, we'll be looking at these and these types of motions and the quantum mechanics of these systems in a lot more detail later on. And then there's electronic energy. And this is just simply the energy of the electrons in the atomic or molecular systems, and that also contributes to the internal energy of our system. And finally, there's the energy of interactions. So we've talked about Coulombic interactions and such that occur between particles in the system. All of these contribute to the internal energy of any kind of chemical system that we're looking at. And of course, the interactions represent, as we noted before, potential energy. And also, as we noted before, rotations and vibrations apply to molecules, but they don't apply to atoms. All right, and then finally we have something called the equipartition theorem, which allows us to calculate average speeds for molecules, and the average internal energy for molecules is a function of temperature. And so we have these situations where this is a classical description which assumes no interactions, like an ideal gas, for example. And so this quantum mechanics will show us that there are some deviations from this that we will need to be concerned about, but right now we'll just take a look at this classical situation. So for a monatomic system, that is one atom, the average internal energy is 3/2 per mole, is 3/2 RT. R, of course, is our gas constant, R, which appears in the ideal gas law, can take on several forms. The most useful form in this particular case is 8.314 joules per Kelvin per mole. So R times T, and T would be the temperature in kelvins, will give us units of joules, okay, per mole. So the average energy of monatomic system, all right, excluding electronic energies, the translational energy is 3/2 RT. The CV is something called heat capacity, and we'll talk about that later on. We'll come back to this. For systems with more atoms, like a diatomic molecule, we have a slightly higher average internal energy because we've got several modes of motion. So the 3/2 RT represents translations, the RT represents rotational energy, and the RT represents vibrational energy here. So we add all those together and we get the 7/2 RT for the average molar internal energy for a diatomic system. We start looking at polyatomics. We actually have to specify whether it's linear or nonlinear and why that is. We'll come to at a later point. But in this case, we have the 3/2 RT for translations and the RT for rotations. Okay, and then for vibrations, the number of vibrational types of motion depends on the number of atoms, n. So we have 3n minus 5 of those for a linear polyatomic molecule. So for example, carbon dioxide, which is a linear triatomic, okay, would have 3/2 RT plus RT, and 3n minus 5, because n is the number of atoms, which is 3. So it's 3 times 3 minus 5, so that's 9 minus 5 times RT. So that's 3/2 RT plus RT plus 4 RT. And that gives us 13/2 RT for the average energy. Now, again, what you'll note, of course, is that the average energy increases as we increase the temperature in all these situations. But I will mention here that this, again, is a classical description. It does not include quantum mechanics. The reality is that the average for molecules like carbon dioxide is lower than what we have classically, and that again is a quantum mechanical effect that we'll talk about in the future. All right, and then for nonlinear polyatomics, We'll notice the difference is 3n minus 6 as opposed to 3n minus 5 for the vibrational energy. We'll also notice that rotations would be 3/2 r as a t as opposed to RT for linear. And again, this is an equal partition theorem. Actually helps us to estimate the average molar energy based on temperature for a molecular system. Again, it is a classical description that does not account for quantum mechanics, and that's something that we'll have to deal with at a later date. All right, so finally, we've got these definitions laid out. As we begin our discussion of thermodynamics, we can get to the first law of thermodynamics, which may have been introduced to you as the conservation of energy law, that energy is neither created nor destroyed in a process. It remains constant. Mathematically, we will represent changes in energy and through changes in internal energy through, again, Q and W, Q being heat transferred. So the change in internal energy is based on the heat transferred plus the work associated with it. And from the differential perspective, which of course is what we're going to need to be considering as we look at systems that undergo continuous change, that we write it du in the differential form equals dq plus dw. So that is how we will phrase the first law of thermodynamics mathematically. This ends our initial discussion of the first law. In the next video, we'll go into these in more detail with some more concrete examples.